In today's video, we're going to take a deep dive into a proof of concept application called GPT Meeting Agent. This example shows a pattern of development that leverages large language models like ChatGPT to create autonomous agents that can utilize your own internal APIs, enabling them to make decisions about your data and how to use your APIs to solve a wide range of tasks. The GPT Meeting Agent is a proof of concept that is largely a generic approach of exposing your internal APIs to large language models or LLMs, so they can make decisions about what APIs to use to solve a specific problem. This will be the first example in a series as we are looking to integrate LLMs to take advantage of various ServiceStack features like auto query and auto forms to speed up the development of automations that use the reasoning capabilities of advanced models like ChatGPT and GPT-4. As a side note, we've created this example to not only show ServiceStack developers how you might build a similar system, but we're also looking for feedback from developers that are looking at or already incorporating ChatGPT and other language models into their solutions. This feedback will better inform us how to best integrate a standalone plugin that optimizes common use cases and provides an easy way to quickly stand up new agents to solve specific problems. In this proof of concept, we not only use the LLM to reason about which APIs to use to complete a task based on the configuration of the plugin, which in this case is to book a meeting for a user, but we dynamically create and populate forms based on which APIs the LLM decides to use. The link's in the description for the full source code for this example, and we will walk through how it works in the rest of the video. Please reach out to us if you are looking to build solutions with AI agents using our Discord, customer forums, GitHub discussions, or just commenting below. This proof of concept has very little bespoke code that's directly related to booking a meeting or the APIs specific to this example. Instead, we are using the ChatGPT API to run the automation that is able to book meetings on the user's behalf by chaining together internal data and API usage. The final prompt that is built from the configuration of the GPT Agent feature plugin in the example and the user-provided prompt is what drives this automation to reach for the APIs to book a meeting on behalf of the user. Before we get to the example and how it works, we're going to go through some high-level background information about what technologies and techniques are used in this proof of concept and how they work to automate tasks using the ChatGPT API. Starting from the beginning, large language models are an advanced type of AI that has been trained on a huge amount of data and a framework of training known as a transformer to create a generative pre-trained transformer model or GPT model. These AI models predict the next token or part of a word in a given text input based on the data it's been trained on. These can be used to build a variety of solutions that take natural language as input. Depending on the type of data these models are trained on, some have the ability to take instructions. The most well-known implementation of this is ChatGPT itself. At the time of recording, the standard ChatGPT model that is used is GPT 3.5 Turbo, and OpenAI actually has an API to access this same model so you can use it in your own integrations. The OpenAI API and other large language model interfaces take an input of a text prompt. This prompt is then tokenized into a sequence of numbers that represents parts of words or tokens. The language model then uses that input to try to predict what token will come next in a given sequence. As these models have become larger and trained on higher quality training data, they appear to have emergent capabilities such as reasoning, which can be used to make decisions to solve complex problems. We can exploit these capabilities by giving these models agency to take actions, creating agents. The concept of an agent is created when we construct the prompt text in a specific way that gives this reasoning capability the ability to take action via commands which are bound to your own service APIs. A way of improving this decision making when choosing which of your own internal APIs should be used to solve a specific problem relies on a technique of prompting called chain of thought. This requires us to prompt our agent for thoughts as output regarding the actions it chooses to make. These thoughts are then fed back into the model in future prompts, creating a chain of thoughts about why each action was taken along the way. This reinforces why previous decisions were made, which influences future decision making. This technique has shown to improve the reasoning ability of large language models or LLMs, which helps the agent break down problems into multiple steps or smaller problems that it can take action on. We then instruct the LLM to only return the following data structure, which contains a thought and a command. The commands are your service APIs, and we provide the agent enough information on how to use them and what's their purpose. The agent returns a command name and a body that represents the values to be populated in a request DTO in JSON format that is then used by the rest of our system. The results of those commands running, e.g. the responses from your own APIs, are also injected into the messages or prompt sent back to the agent on the next run. This technique is called in-context learning. By providing additional internal information about your systems, the agent model takes that information into account when making future decisions. All these techniques are a part of what people call prompt engineering. I'll leave some additional links in the description if you want to dive into this further. There are a lot of great YouTube creators following this technology, as well as plenty of well-written tutorials and scientific papers to help you along your way of leveraging these techniques when building your next solution that requires a natural language interface. One of the biggest advantages of using this technique to invoke your own service APIs as integrations is that you aren't bound to the OpenAI API. That is what we're using in the GPT Meeting Agent, as OpenAI does currently provide the best large language models and easy access to them. However, the open source ecosystem of large language models is developing very quickly, and it is expected that a lot of domains like finance, science, programming, and others will benefit from having specialized models. Being able to integrate your own APIs quickly without relying on a third-party plugin system gives you the flexibility to build solutions with the best model for your domain. If you're interested in seeing videos that use these technologies further or dive into related topics, let us know in the comments below and what specific topics you would like to see. Now we have some of the background about the technologies and techniques that are used in this proof of concept. Let's dive into the GPT Meeting Agent example to see how it all works. Let's say you want to book a meeting with Lynn, a member of your team. We could do this with a single message to our agent reading, "I want to have a meeting with Lynn regarding marketing plan on Saturday the 6th, sometime in the afternoon." The GPT Meeting Agent then has enough context to reach for the right API endpoints as tools. This context comes from how the agent is configured when registered on the server using the GPT Agent feature plugin, where the role, prompt base, and name all inform the behavior of the agent. Which of your own API services you make available to your agent is also controlled here through the use of matching tag attributes. In this chat example, it will use the search users API with the name that the user has provided, Lynn, to quickly identify who Lynn is in your staff and gather the necessary information. Next, the agent infers from the prompt that it will also need to use the get user schedule API to analyze Lynn's availability for the upcoming week or around the time of the requested meeting. meeting. The agent can then use data from your own services to combine with services it decides to use in subsequent steps, enabling the ability for the agent to solve more complex problems with multiple sources of internal data via your own APIs. Lynn's user ID is extracted from the Search Users API and then passed on to the Get Users Schedule API. The forms we are seeing in the GPT Meeting Agent UI are being dynamically created based on the APIs the agent decides to use and populated with data coming from the agent as well. These use the AutoForm component from the ServiceStack View library. They are not specific to this example, so can be used with your own ServiceStack APIs as well. Also in this example, it's the browser client that's actually the one chaining these actions together, making those subsequent calls referencing the same task from the first chat interaction. We can see in this flow diagram where the responsibilities are separated between your browser, ServiceStack server, and agent, in this case powered by the OpenAI's GPT 3.5 Turbo model. The agent is tasked with the decision making based on your user's prompt and your own configuration regarding which of your own registered APIs the browser should call and pass back that information to the agent via the ServiceStack integration. Each time the agent wants to run a command, we also show a web form equivalent to that API command. This just acts as a visual representation of what action the agent wants to take. If you need to put in additional guardrails for your agent that will require manual user input with the use of specific APIs, we can use the confirmation required attribute, which is applied to your request DTO. This protects specific endpoints from running automatically in a generic way, and we can hook into the browser workflow to handle the submission of specific APIs like Create Calendar Event to customize the behavior of our browser front end with very little code. In this case, we are tagging the task as completed when a submission of the Create Calendar Event autoform is made. To better illustrate the flexibility of this agent, let's show a more realistic interaction, one that you're probably more likely to see with something like a voice-to-text integration. Here we are intentionally being very short with the agent, forcing it to ask us questions. The agent asks for information based on the input of the API it knows about. We can progressively provide information, even changing our mind along the way, and we will get to the result of being able to book a meeting. The agent is making independent decisions based on the messages we build up in our system and send to it through the ChatGPT API. To better illustrate this, let's see how the agent changes its behavior when we alter the APIs it can access. Currently, the agent has access to 3 APIs: Search Users, Get User Schedule, and the Create Calendar Event API. If I use the prompt, I want to have a meeting with Katrina regarding sales report on Friday the 5th sometime in the afternoon, and then add the phrase, please ensure that the meeting room has a projector, the agent will likely process this request as normal by searching for a user, requesting the user's schedule, and then constructing the Create Calendar Event request. Because as of yet, none of our APIs mentioned meeting room, projectors, or resources. But if we then add a new API called List Meeting Rooms as an auto-query API, tag it with Teams, and give it a relevant description, our agent will now be able to access this API as the plugin will discover the new API with the matching Teams tag. We will also add a Meeting Rooms ID property to our Create Calendar Event Request API, and then prompt the agent again with the exact same prompt. The agent searches for our user and gets their schedule like before, but instead of jumping straight to the Create Calendar Event API, it runs the List Meeting Rooms API and chooses Meeting Room 3 as it has a projector listed in its resources. Again, all we did was describe what the new API does, tag it to be included in the APIs that are injected in our agent's prompts, and it will attempt to reason about when it should reach for each different API. If we don't mention the meeting room, it will either not populate the meeting request ID or populate it with a random number. So why is this useful for API developers? This plugin simplifies the process of incorporating AI-driven natural language interfaces into your application, making them more intuitive and accessible for end users. We are keeping the manual prompt editing to a minimum by generating the service commands that the agent can access using your own ServiceStack services and your related metadata. All of this information about your services and other information is fed into a prompt or series of prompts sent to the ChatGPT API to produce the results we see. Now that we have some background, let's walk through the ChatGPT plugin in this example to see how it works to make these ideas more concrete. First, the plugin uses metadata from the ServiceStack APIs to inject information as service commands into the base prompt. It takes the description tag and the request DTO name and generates a TypeScript definition to describe the structure of data the command expects. Since these service commands are your ServiceStack APIs, this TypeScript definition matches that of your request DTO. The GPT Agent feature plugin then takes these definitions and injects them into what we call the base prompt. The base prompt example text file in the prompts directory of the example project contains some generic aspects to the prompt to help make the agents behave more in line with what we need to integrate our ServiceStack APIs. Here we can see the prompt is broken down into sections: constraints, commands, which are internal commands to assist with memory and asking questions of the user, service commands, which is where your ServiceStack API definitions are injected, and finally the expected format of how we want the agent to respond. A lot of this is inspired by early work of the AutoGPT project, modified for this example and integrating with ServiceStack APIs. The command and body in the response format is where our integration happens. We match the command name with a registered request DTO, and the body is used to populate that request. We also inject messages from the user that include the role and name of the agent, which is configured in the ChatGPT feature plugin. These properties are important as they instruct your agent on what role you want it to play in an interaction with users. Lastly, each request has a message that ends in the phrase, "Determine which next command to use to complete tasks. You must respond in the JSON format specified above." Messages are in order of importance, where the last message in the list is the most important or relevant to the current query. Each of these interactions is initiated from our browser when the client clicks chat. We're sending a request to one of two services which are a part of the ChatGPT feature plugin. When a service command is returned from our OpenAI agent, the browser makes that request and sends the response back to the plugin service so it can be injected in the message history sent to the OpenAI agent. As this history builds up, so does the number of messages we are sending to the OpenAI API with each interaction, giving our agent more and more context with each additional interaction. There is a limit to this context, which is measured in tokens, specifically around 4,000 with the GPT 3.5 Turbo model. So we calculate the number of tokens before making the request and only append message history where there is room in the context for it. Which brings us to limitations. There are a few others that should be considered if you are interested in using a similar approach in your own projects. While the decision-making ability of the OpenAI models is very impressive for AI, it is far from perfect, and depending on the prompt, it will make some strange choices which can be frustrating for users. Another limitation is the more complex your service request DTO is, the less likely it will be used correctly. So currently, the plugin only supports flat request DTO structures with primitive types. Also, if your API responds with large nested responses, this can not only take up valuable context space, it can confuse the agent as well. We have a way to address this currently by using the register command filter method on the plugin itself. This will allow you to transform your API responses into a different structure that is then injected into the message history, so you can help your agent focus on what information is important. Despite these limitations, this technology holds great promise for a lot of different applications, and by using generic components both on the server and the browser, ServiceStack provides the ability to bring it all together, introducing a new way that lets GPT agents use APIs and their related UIs together. To better explore some of the possibilities, we plan on building a series of example applications using this technology based on different use cases. And this is why we'd like to hear from you, the ServiceStack developer community. We're eager to learn about the use cases and scenarios where you envisage using a similar approach with ChatGPT and ServiceStack integrations like we've demonstrated here with the GPT Meeting Agent. Your feedback will help us develop a library to make this approach even easier to implement within the ServiceStack framework. Additionally, it will enable us to explore different flexible approaches to solving real-world problems that you, as developers, are facing when working with cutting-edge technologies like ChatGPT. Please share your thoughts and ideas and use cases in the comments section below, or reach out to us through our Discord, GitHub discussions, or customer forums. And as always, thanks for watching.